So today we have our own Sandro Tacchella. He got his PhD in astrophysics from ETH Zurich, working with Marcelo Carollo in 2017. And this thesis got him the ETH Medal for Outstanding Doctoral Thesis, as well as an EA Muller Award for Best Thesis from the Swiss Society for Astrophysics and Astronomy. Since then, he's been a CfA fellow here with us, and today he'll be telling us about star formation, how it's regulated, and how it varies. Please take it away.
Okay, well, thank you very much for the introduction. Very excited, to talk to you today about the regulation of star formation across cosmic time. So first, I would like to thank you all for zooming in, but also, of course, all my collaborators over the time. Here is a list. I don't think that's the complete list, but that's the main collaborators over the past few years. And you can see many of them are actually at the CfA. So I must say, of the last 2.5 years, I've been to the CfA. I had really a great time, and I'm very thankful for all of them to collaborate with me and do some great science together. So I myself, I'm very fascinated by images such as those where we see that galaxies, even kind of in close proximity, seem to be very diverse. So galaxies come in a wide range of different shapes. Some of those galaxies have star formation, some galaxies don't. And I'm really interested to understand why galaxies are so diverse in today's universe. And we can basically see that the star formation usually in galaxies takes place in kind of a disk-like configuration, as shown here. And then you also have spheroidal-like components, usually in the centers of these star-forming galaxies, which we usually call the bulge. But sometimes also the spheroidal component can dominate the whole structure of the galaxy. Now, we can see already in this image that this galaxy seems to be a bit bluer, this galaxy seems to be a bit redder. And so we can really quantify how many galaxies have kind of red colors, meaning like little star formation or no star formation, and galaxies that have a lot of star formation or blue. And so this figure has been taken from Kevin Chavinsky's paper in 2014, who computes the U-R color, thus corrected from SDSS, and plus the stellar mass. And you can see that, we have down here these blue galaxies. We call them sometimes, blue cloud galaxies. So these are the star-forming galaxies. And up here we have the red sequence. So these are usually the red galaxies that have little or no star formation. And you can see that, we have in between nearly not an empty region, but kind of there is a clear bimodality in this color plane. And the Milky Way is kind of, I would say, a typical star-forming galaxy, rather massive here, sitting kind of in between, kind of going through what you usually call the green valley onto the red sequence. And so, this is kind of what we see when we look at star formation or colors of galaxies on integrated scales. We can, of course, also split the galaxies according to their morphology. And so Kevin did his paper is basically using Galaxy Zoo to classify galaxies as early type galaxies, so galaxies with no spiral arms, and galaxies that have some kind of spiral structure, which we usually call the late type galaxies. And you can see that the early type galaxies are clearly up here in this red sequence, and the late type galaxies are dominating this blue cloud down here with kind of extended arm, through the green valley. And of course, it seems like, oh, these red galaxies seem to be quite boring, but if you would look at their dynamics, you actually can see that these galaxies also show a lot of diversity. So some of these galaxies are indeed rotating quite quickly, so we call them usually fast rotators. There is an indication that these galaxies have also rather disky isophotes, rather steep metallicity profiles, and all this shows you that this was a rather gas-rich formation process. Whereas when we look at galaxies at the top end of the mass function, so kind of these massive galaxies up here, they're usually rotating quite slowly, and they have boxy isophotes and rather shallow metallicity gradients. So this shows you that these galaxies might have formed rather without with little gas and rather through gas-poor mergers. Now, this is a picture that we see today at redshift 0, and it's clear that we cannot learn everything from such a diagram. It's clear that these red galaxies up here, they were star forming in the past, so somehow they were probably down here somewhere in their past. And so what we see in such a diagram is basically the integration of galaxy evolution over the past 13 billion years. And so what we really want to do is to look at earlier cosmic times to understand how really galaxies build up their stellar mass and how star formation is proceeding galaxies. And so what I'll show you here is such an image. This is the Hubble Space Telescope Deep image, and you can see here that we see a lot of different galaxies, and some galaxies are very large, some galaxies are very small, and also quite red, which means they're probably quite far away. And so thanks to such deep surveys over the past 10 to 30 years, really gained a lot of understanding of how the stellar mass is distributed in galaxies and also how star formation is distributed in galaxies. And so what I show you here is basically an integrated diagram. This shows you the star formation rate as a function of stellar mass at different epochs. So this is kind of close to today, redshift 0 to 0.5, and then we go to higher and higher redshifts to earlier and earlier cosmic times. And what you can see is that there seems to be in this log space a linear relation between the star formation rate and the stellar mass of a galaxy. And the overall normalization seems to increase when you go to earlier times. You can see this nicely here. At a given stellar mass, the star formation rate was higher at earlier times. And you can also see that this relation is quite tight, and that's why it got its name. Some people call it the star forming sequence, some people just call it the star forming sequence. But this relation, I will discuss this relation quite extensively in my talk today. But it's basically a relation between the star formation that we measure in a galaxy and the stellar mass. And you can see that the scatter has been measured by many different people over the past years. And people usually come up with estimates of somewhere between 0.2 to 0.3 dex. And this seems to be rather mass independent, at least above 10 to the 9 solar masses, and also quite epoch dependent. So this is now basically on global scales across cosmic time. But we of course know that star formation is a very complex process acting on many different scales. So we have these large scales where we discuss the gas inflow, but then of course we can zoom in on individual galaxies in the local universe, or as here on the Milky Way, where we see that the star formation really takes place in rather small entities, which usually called the giant molecular clouds. And so here we are specifically zooming in on Westerlund 2, which is a young star cluster of the age of about 1 to 2 million years. It's about 20,000 light years from the Earth. And you can see that, it's a very, very messy region, right? So we have the H2 regions, we have the young stars that really act on the gas and pushes out some of this gas. And so, it's not just that we can just study integrated constraints. If you want to understand star formation, we really need to understand all the scales, not just the overall global scales in galaxies. And so the key questions that I try to address in the next few minutes are the following. So which physical processes are really responsible in regulating star formation? And I will see that, I'll show you this is really, trying to incorporate small and large scales. A bit more specific, and I will motivate this question a bit more, is like also the scatter in the star forming sequence. So in this relation between the star formation and stellar mass, what is really, determining this scatter? Is it short-term fluctuations on short time scales, or are these long modes where galaxies oscillate about some equilibrium? Then a second question will be, of course, related to quenching, to the cessation of star formation. We have seen before we have blue galaxies, but we also have a lot of red galaxies. So how do galaxies basically cease their star formation is one of the big open questions in galaxy evolution. And the third question is, how is this all related to structure and the morphology of galaxies? So how are we able to make slow and fast rotators, early type galaxies, as well as spiral galaxies? So I was kind of ambitious when I put out these questions, and I think we have a lot of time to discuss the first one. And if time permits, I will go to the second and third question, but we will see how we proceed in the talk, I guess. So the key message I would like you to take away from today's talk is really that I think galaxies are a unique laboratory to study the physics in galaxies and also beyond galaxies. So, there are a lot of processes acting on small scales, as star formation, the young star cluster formation, H2 regions. But then also we have processes that not act only on the galaxy scale, where we have, spiral arms and bars, but we also have then, of course, the environment of galaxies. And that we know that galaxies live in dark matter halos, and there's a large, scale structure that determines parts of how galaxies look like today. And so I think galaxies are really this nice laboratory where we can study a lot of different physical effects from small to large scales. Now, I would like to just highlight a major limitation observations. So as observers, when we look at galaxies, we are really limited to cross-sectional studies. This means we can observe each galaxy only once during its lifetime. And so this means that when we look at galaxies today and we look at galaxies in the past, these are not the same galaxies. And one has to be very careful in order to infer something of how an individual galaxy evolves. because we usually relook at different samples. And so we have really, it's really difficult or impossible basically for galaxies to do longitudinal studies where we can basically look for one individual object, how it evolves through cosmic time. And so this is a limitation, I think, that comes in from observations. And that's why I'm also very much in favor of having this integrated approach where we use analytical and numerical models at the same time as observations to really learn about the physics of galaxies. So regulation of star formation. So I will start out now with a rather simple, some simple considerations and build on top of that through the later slides in my talk. So if you think of a galaxy living in a dark matter halo, it has some gas, it has some stellar mass. We can write some very simple equations. We can say, for example, that the gas reservoir in a galaxy is fed by some inflow rate. Then some of this gas mass gets turned into stars. So we can write the star formation rate to be, proportional to the gas mass divided by the depletion time. So this is motivated by a Kennicutt-Schmidt-like relation. And then we can write something for the outflow of the gas reservoir. So there are winds, usually, or even, winds from stellar feedback or even from HENs. And we can assume, for example, that this outflow rate is proportional to the star formation rate via the mass loading. And so if we write down now an equation for the conservation of mass for the gas reservoir, we end up with, what people usually call the regulator model or a bathtub model. And so, why is this called the regulator model? You can basically see from this equation, from this picture, that when the inflow rate goes up, the gas mass in the reservoir goes up as well, and therefore also the star formation rate becomes larger. However, because when the star formation rate gets larger, at the same time, the consumption rate of this gas reservoir increases. You have basically, a higher star formation rate, as well as you have, because the star formation rate is high, more outflows, and therefore, basically, the growth of the gas mass gets lower again. And so you have this basically self-regulation picture that comes up from the simple mass conservation very naturally. Now, if you introduce a timescale, which is called the equilibrium timescale, which is just basically proportional to the depletion time divided by the mass loading, you can rewrite this equation in the following differential equation, for the star formation rate. And you can see that the star formation is roughly proportional to the inflow rate. And this equation here, we will go into the details much more in the next few slides. But basically what you can see when you solve this equation, there are simple solutions that basically show you when the inflow rate goes up, the star formation rate goes up, and then usually exponentially declines back over the equilibrium timescale to the equilibrium star formation rate. Now, many people, have explored these kind of models in the past years, and a lot of people have assumed different things of like ignoring one or the other term, as well as basically thinking of rather smooth accretion histories related to dark matter. And we also explored this. So, with Sandro in 2018, we looked into, when we look at the simple, dark matter merger histories from dark matter only simulations, we basically write down that the star formation of a galaxy living in such a dark matter halo is proportional to the inflow rate, which is proportional, we assume, to the dark matter accretion rate. And so we can write a simple equation that says, well, the star formation of a galaxy that lives in a dark matter halo mass of mh, the given redshift, is equal to some star formation efficiency times the dark matter accretion rate times the baryon fraction. And so this is a very, very simple approach. And we hope that we can basically rule out such a simple model. And so here the star formation efficiency, as as defined here, we assume that it's redshift independent. And we basically, it's basically a star formation divided by the dark matter accretion rate. And so if we do this and we basically, we basically calibrate the model, basically the star formation efficiency is the only free parameter in the model. We calibrate it via the UV luminosity function, redshift 4. If you're interested for like the high redshift universe, we can basically find something like this, where the star formation efficiency peaks around the halo mass of 10 to the 11 solar masses and declines towards lower and higher masses. And so such a simple model where you just plug this in, and now you basically paint such simple galaxies onto these dark matter histories, you immediately get out very nicely a match to the UV luminosity function at high redshift. So from redshift 4 up to redshift 10, as well as what we have on current constraints for the stellar mass functions. And so you see that such a very simple model that really focuses basically just simple on structure formation from a dark matter halo formation point of view, is able to reproduce current observational constraints quite well. Looking into star formation a bit more, I show you here the cosmic star formation rate density. So, the star formation rate per unit co-moving volume. And you see this is our observational data, and here you see our model, and it naturally goes through these points quite nicely. And you can see that there is a rather steep decline of the cosmic star formation rate density when we go out to redshift 10 and 14, which is of course an interesting regime coming for JWST. So hopefully in the next few years we will be able to understand the star formation at this epoch in much greater detail. So why is there such a strong increase? So such a simple model can give you quite a nice intuition of why things look as they look. So for example, here what I show you is the star formation efficiency again, which peaks around this 10 to the 11 solar mass halos. And what happens here for this increase basically is that the halo mass function, which the units are shown here on the right, the halo mass function is moving into this a regime where you can form galaxies quite efficiently. So the M star basically moves into this regime of of high star formation efficiency, and this makes this increase of the cosmic star formation rate so dramatic. The nice thing is also that one can explore, this I've done with Rohan Naidu, he's a student here at Harvard, to study, for example, ionization. So you have a good model of how the star formation proceeds in different dark matter halo masses, and then you can ask the question of how needs the escape fraction be distributed in order to reproduce the IgM neutral fraction as a function of redshift. And what we find is that actually if you want to have a late and rapid ionization, massive or bright galaxies need to play an important role in reionizing the universe. So you can look up this paper if you're interested to learn more about this. So such models are able to reproduce the overall evolution of the cosmic star formation rate density quite well. So again, the increase at early times can be understood by number density of basically halos that are able to host star forming galaxies that can form stars efficiently increases. And then we have the peak around redshift 2 or 3, where basically most of the stellar mass in the universe forms. So roughly between redshift 1 and 3 are 50% of all the stellar mass formed. And then we have the decline at late times, which is related to the drop in accretion rates onto galaxies, as well as some galaxies seem to totally stop their star formation, which we usually call quenching. And now we can go one step further and not just look at the cosmic star formation rate density, but we can also look, for example, at the star forming main sequence. And it's quite interesting. It's actually pretty hard to not reproduce the star forming main sequence in such models. And so basically you always find a relation between the star formation and stellar mass. And this is mainly because overall the main sequence is really given probably by the accretion rates of dark matter halos and therefore of baryons on long time scales, but even the scatter. And I would maybe argue that this is a coincidence, and I would come back to this later in my talk. But basically, it seems that the main sequence scatter is very comparable to the scatter of dark matter accretion rates. So this is taken from Aldo's paper that shows the mass accretion rates as a function of real mass of the halo. And you can see that the scatter of this, so the scatter in the accretion rates of dark matter is very comparable to the scatter in the star forming main sequence. And so I would argue maybe this is a coincidence, but we will discuss this more in the next few slides. And so now, of course, the question comes along, is like, are we already done? And the answer is, of course, no, because I didn't really discuss the physics that shapes the star formation efficiency. So most of these models have some kind of a star formation efficiency that is parameterized as a function of halo mass. And it looks something like this, but then of course the question remains, what is the physics? Why are halos that are in this regime able to form stars more efficiently than basically galaxies down here? And over the 10, 20, 30 years, the big physical effects are usually called the stellar feedback as well as black hole related feedback processes that basically are believed to regulate the growth of structure at low masses and or at high masses. But there are of course many other processes related to these phenomena, including mergers, cloud physics, or really small scale physics, are spiral physics, and reaccretion of outflows, cosmological accretion. So there is a lot of different physical effects all acting to basically describing the star formation rate of a galaxy. And so we can order these, roughly as a matter of scales. So we have here these large scales, where cosmological accretion and mergers are playing an important role. And then we go to smaller and smaller scales, as I showed you, at the beginning, basically cloud physics plays a role. So we have here the spatial scales, but of course, these also translate into time scales. So we have here rather long time scales at work, so of the order of gigayears. And then when we go to the smaller structures, we of course talk about millions to tens of millions of years. So these are rather short time scales. And so all of these things basically act together. And so for example, mergers induce, of course, a lot of star formation, and which then, create a lot of clouds, and then we have stellar feedback, and so on. So there is a lot of connection between all of this. And so that's where we end up with, the star formation histories that are not just simple, lines, but actually look quite complicated. So these star formation histories can be very variable. So it can go up and down over different time scales. And so the idea of the question is now is how can we learn about these kind of physical processes if we would have this kind of information. So if you understand the variability of star formation in galaxies, would be able to learn something about these physical processes. And so basically, that's what I show you here is this distance from the star forming main sequence. So this is the relation between the star formation and stellar mass I've shown you before. And so this basically quantifies whether a galaxy is above this relation or below this relation. And so galaxies up here, they would be basically forming more stars than per unit time than galaxies below here at the given stellar mass. And so the question remains, like, how do galaxies fluctuate about the star forming main sequence? So are they basically moving on these short time scales or on these longer time scales? And so we can ask the question, is basically the scatter of the star forming main sequence driven by short-term fluctuations or long time scales? And again, I motivated this based on the physics of star formation, but from a galaxy evolution point of view, especially for observers, it's also important because of the interpretation of scaling relations. And so I just want to basically highlight this with a simple cartoon. So now we have this distance from the star forming main sequence as a function of mass. So we say we have a galaxy at redshift 0, and now we're following it back in time, looking at how galaxies moves about this relation. And so maybe at later time at redshift 2, the galaxy will sit somewhere here. So it moved up and down the main sequence several times on short time scales, and now it has a lower stellar mass. There might be another galaxy starting at the same point, so at redshift 0, and moves up and down also several times, and then ends up here. And then you can move on, of course, and you can say, okay, at earlier times, how does it look? And galaxy keeps still moving up and down, and you will end up with the galaxy over there, and the last one will end up over there. And so the point here is, what you can see is that, yes, so galaxies move up and down the main sequence. So at each instant in time, they might have quite different star formation rates, but the overall star formation history, the mass growth, is basically very similar. And so what then observers can do is they can say, okay, I've measured a galaxy on a scaling relation, now, for example, on the star formation stellar mass relation. And we can basically follow this overall relation back in time. And the main sequence then basically gives you a good representation of the average star formation history of a galaxy. So we can say that equal mass galaxies today, you can take, for example, the Milky Way, and the galaxy that has a similar mass like the Milky Way, have quite similar star formation histories. And so maybe at redshift 2, they also have a very similar mass. So this is when oscillations happen on short time scales. If you go to longer time scales, there is a problem. As you can see now, I'll show you a case where a galaxy basically stays below the main sequence for a very long time, and then there is another galaxy that might have stayed much longer above the main sequence. And so the mass at the end of these galaxies, you can see is quite different. So the galaxy above the main sequence had always higher star formation rate than the galaxy below. And so this means that basically this galaxy will have much smaller mass in the past to end up at the same stellar mass today. And so this means that basically the main sequence is not a good representation of the average star formation history, and equal mass galaxies have actually very diverse growth histories. And so I would say that, we have the physics of star formation that is really, gives us a lot of interest to study the scatter around the main sequence, but then we also have, interpretation problems maybe when we have these long time scale oscillations. And so I was thinking a lot about these oscillations, and then my good friend and also collaborator Nevin Chapler, was doing a lot of HGN light curve modeling during that time. And so then we came up with the idea that maybe we could quantify this variability via the power spectrum. Okay, so you basically take the power spectrum of such a time series and try to understand how much pi do you have on short time scales versus on long time scales. So for example, here, such a curve has a lot of power on short time scales, whereas such a curve has more power on long time scales. And so, so let's see. So basically, I want to give you first some intuition. So we start with building a very simple model. And this also has been done in collaboration with John Forbes, who was here at the CfA and moved recently to the CCA. We basically want to build some intuition for this by studying again this equation here. And what we do now is basically say, okay, before we had these sort of smooth accretion histories, mainly dominated by the dark matter accretion rate. what is if we now feed the galaxy stochastically? So what happens if we feed, we modify this term here on the right and assume that the inflow rate is basically a stochastic process with a certain power spectrum density. And so then this gets basically a differential, stochastic differential equation. And so I want to show you first a very simple case where you can see that the inflow rate here is very strongly variable, and the resulting star formation looks something like this. So this is just numerically integrating basically this equation up here. So what we assumed here is basically that the power spectrum density of this inflow rate is a constant. So this is a so-called white noise process. So this is just a constant power spectrum density. You can see that as a function of frequency or time scale. Basically, there is equal amount of power on all frequencies or time scales. And so this means that basically you have a lot of power on short time scales. So the inflow rate is very variable. And now we can compute what the resulting star formation rate is. And in this case, actually, there is an analytical solution to that. And the power spectrum for the star formation rate can be expressed with this equation here, where you can see that basically that the overall normalization of the power spectrum is given by the variance of the inflow. And then on shorter time scales, you basically have this break in the power spectrum. And so this is usually called, a damped random walk. So when you solve this equation, you end up with a damped random walk. So you can see that this is basically acting as a damping term, and the equilibrium time scale. So the time scale that tells you how quickly you are able to, basically converge back to the equilibrium star formation rate is playing the crucial role. And it's also imprinted in the power spectrum. So the interpretation of this is that basically on short time scales, okay, on large frequencies, you basically correlate the star formation rate, and you correlate the star formation rate with a power law slope of 2. And then above a time scale that is 2 pi the equilibrium time scale, you basically decorrelate the star formation history. So basically what this means is that you are throwing gas onto the galaxy. So you throw a package, a package of gas, the star formation rate goes up, and then it exponentially declines back onto the equilibrium time scale. And so basically you correlate the star formation rate typically over this equilibrium time scale. And this is exactly what we can observe here in the power spectrum. And so you can, expand this. You can say what happens if the inflow rate, the power spectrum of the inflow rate is even more complicated. And so we have explored this. And what you basically can see is that in this simple model, that, you always correlate the star formation history by a factor of 2, or by, an addition of 2 in the slopes. And you can see that basically now from left to the right, the inflow rate gets more and more correlated. So we have this tau x, which marks the break of, it's basically the correlation length in the system for the inflow rate. It increases to higher and higher times. And you can see that, we set the equilibrium time scale to be the same, and you're always correlating the star formation histories on shorter time scales, and the slope difference here is just 2. So now we have then expanded basically that model, and I don't have time to go into all the details, but basically what we were doing is now, instead of assuming that the star formation is just proportional to the gas mass divided by some depletion time, we basically assume that the star formation rate is sustained by GMCs. So basically we have this gas reservoir, and then we are randomly sampling based from a mass function for GMCs, the star formation rate. So we basically, have an additional contribution to the star formation variability that basically models the small scale processes. So we have the variability coming in from these large scales, from the inflow, but at the same time, we basically have these small scale processes, which we now, choose to be rather close to observations, empirically driven basically by a mass function, where we just sample the GMC population. And so the corresponding power spectrum looks something like this. Again, this is basically showing you that on long time scales, typically, the inflow rate is is basically giving you the shape of the power spectrum. And then on this intermediate time scale, the gas cycling, so the regulator model itself is playing the crucial role. And then at the short time scales, we have this additional contribution coming in from the stochasticity of randomly sampling GMCs. And the nice thing is that we have not just a numerical understanding, we also have analytical understanding for how things evolve in this model. And of course, you can play around with the different time scales. But the key takeaway here is that on short time scales, the break in the power spectrum is basically related to the average lifetime of GMCs, which is quite interesting because this means that maybe we are able to learn something about GMCs from integrated galaxy constraints. And then intermediate time scale, break is related to the equilibrium time scale of the regulator model. And then on long time scales, we have something which is basically given by the accretion rate onto the galaxy. Just very briefly to give you some examples. So I show you here 4 different kind of galaxies. Again, this is rather approximate. We have here a dwarf galaxy regime, a Milky Way regime, a galaxy noon regime, as well as a high redshift regime. And we choose basically input parameters for the inflow rate to reflect these different regimes. So we have, for example, let me go to high redshifts. We have overall higher accretion rates, as well as the inflow rate might be correlated over shorter timescales. Because the halo timescale, dynamical timescale in the halos are shorter. Then we have a prescription for the mass loading as well as the depletion time in the galaxies. And then at the end, we also have a prescription for GMCs, which mainly reflects the mass function, the star formation efficiencies of individual GMCs, as well as their lifetime distribution. And so we put in basically numbers motivated by current observational constraints. And what we get out are basically star formation histories in these different regimes that look quite different. So this is, for example, for the dwarf regime. So this is a star forming dwarf galaxy that has a rather bursty star formation. You can see here in the local universe. And you can see that burstiness here really comes from having this contribution from this GMC power spectrum. So here's again star formation history. This is the power spectrum. The red lines basically shows you what we measure in these different realizations of the model, and the orange are analytical predictions from our model. And you can see that basically here the GMC component plays really a crucial role. So a lot of these fluctuations comes in because we are randomly sampling the GMC mass function. If you go to something like the Milky Way galaxy, it's overall less burst. You can see that the star formation changes over longer time scales more significantly. And this is mainly because the GMC component is not that prominent anymore. And the component here, basically dominates that is related to the regulator model. Then we move on to the galaxy at cosmic noon. There basically, the inflow rate is playing a crucial role. And so this variability that you can see here is really dominated by the variability in the inflow rate itself, as well as when you go to even high redshift, this component is even more dominating. And because the dynamical time of the halo gets shorter, and we assume that basically the correlation length in the inflow rate gets even shorter, you can see that the variability here is quite strong. So the star formation history is very bursty. And again, this burstiness is different from the dwarf galaxy regime. This burstiness is really driven, at least in our model, because the variability of the inflow rate, and not because you're sampling individual GMCs. And so now you can look at these different galaxy regimes and look at things such as the distance from the star forming main sequence. How do galaxies evolve about the main sequence? And not too surprisingly, you can see that in dwarf regime, galaxies move all over the place. So with time, they're moving up and down the main sequence very significantly. Whereas when you go to something like a Milky Way case, galaxies move much more smoothly around the main sequence. And so what we can measure now is the scatter in the star forming main sequence, and compare this to some observational estimates of the measured scatter in observations. And so what I show you here is basically the averaging timescale. So over which timescale do you average the star formation rate? Basically this is like compare this to, for example, H alpha. When we use H alpha as a star formation rate tracer, we are basically sensitive to rather young stars. On the other hand, when we use UV plus infrared, we are tracing basically older stars. And so these are, of course, rather approximate, but you can see that, we measure, for example, for dwarf galaxies, a much, a larger scatter in H alpha than, for example, in the UV plus infrared. And our model nicely is consistent with this. And this is because basically, when you're on short time scales, we see all these small bursts in the dwarf regime very well. But then when we average over a longer time scale, we basically average over several such peaks, and the overall scatter measured in these oscillations are getting much smaller. And so this can be seen here quite nicely numerically. But in our paper last year, basically also drive an analytical derivation of this effect. And you can see that overall these regimes match these observational estimates quite well. Motivating JWST, basically, you can see that here in the high redshift regime, we don't have really a good measure on the scatter at the moment, and redshifts of, let's say, 6. And so JWST, because we will be able to measure H alpha, we'll be able to get a constraints on the burstiness of these high redshift galaxies through the H alpha star formation rate measurements. Okay, there are a few other implications, and I don't have time to go into the details, but I'm happy to chat more about this. One thing is that, as I said, like the break on short time scales in the power spectrum is related to the average lifetime of GMCs. And so there is the hope that we are able to really constrain the average lifetime of GMCs through the power spectrum in the future, and therefore get a handle on the life cycle of GMCs also from integrated constraints. And this is, of course, important because we learn a lot about GMCs based on the Milky Way and in local galaxies, but we really would like to learn more about them also at earlier cosmic times where we are not able to resolve GMCs with the current instrumentation. Another neat thing is when you look at galaxies at redshift 2, you see that they are usually very clumpy. And in our model, at least, such star-forming clumps can be well explained by just the high mass end of the mass function, and not by, for example, combining smaller clumps into larger clumps, basically an observational effect. So this was all based on very simple considerations, based on basic analytical modeling. Now I want to move on to numerical simulations. And what I show you here is a nice figure from Dylan Nelson's paper that basically shows you the baryon mass resolution. So up here are objects that have high, or simulations that have a high resolution. And then we have here the number of galaxies in the simulation box. And there are these two regimes where we basically call this the zoom regime, where galaxies are basically, we have only very few galaxies in the simulations, but they have all a very high resolution. And then there is the other regime, which is sometimes called the box regime. So those usually are simulations that have thousands, 10,000s of galaxies and have a slightly lower resolution. And of course, you want to study both of them in order to understand, what's the physics that drives galaxies. And so with Kartik Iyer, who is now a postdoc in Toronto, I started working with him 2 years ago in the Kavli Summer School. And so basically there, we looked into different numerical simulations, as well as semi-analytical models and empirical models to understand exactly the variability of star formation. And we basically show you results for all these kinds of simulations. You can see here, this is Illustris TNG. Of course, we're well-known models here at the CFAs. And then we have also other simulations that are all kind of these large box simulations. And then we also have a few simulations where we basically have these zoom simulations with the high resolutions. And so how does the power spectrum look like in these simulations? And I show you here, TNG, Illustris, Mufasa, Simba, and Eagle. These are, again, the box simulations. And you can see that, they're not too crazily different, but they show quite some diversity. And you can see that on long time scales, there is in different simulations, there is a different mass dependence. But overall, they all agree that basically most power is on long time scales. And then you have, in some simulations, this hump, okay, this kind of flattening at this kind of giga-year time scale, and then it declines again towards shorter time scales. And you can see that, in Simba, Mufasa, as well as in Eagle, you don't see this decline as strongly. And the overall features here are slightly different. But what I want to highlight also maybe is a detail, but it's that we have these dashed lines which shows you the mass resolution in simulations. So the lower the mass resolution in simulation, the more difficult it gets to probe the short time scales, because you basically have the Poisson noise playing a role. And we have basically tried to forward model the whole process and make sure that our results are not affected by this kind of effect. And now, of course, it's interesting to understand how other models look like. So this is the semi-analytical model, and this is a universe machine. And it's quite interesting to see that, for example, the universe machine, there is overall less structure in the power spectrum. And you can basically see that there is basically just a straight line for the most massive galaxies, maybe similar to like TNG, where you see when the most massive galaxies have a rather featureless power spectrum. And then we can go to Fire, which shows you, and Marvel, so zoom in simulations that show you that there is this flattening up to these timescales. And so kind of more similar to Simba Mufasa. Again, that's not surprising because the feedback process in these simulations have been tuned to reproduce something like Fire. Okay, now, of course, it's interesting to focus on these simulations here, on the zoom simulations, because we're able to basically, go further down on timescales. So when we do this, we can see that, you can see here, this dashed line shows basically the limit. We were looking at the power spectrum in those simulations. You can see here that the flattening here is actually just something that goes up to about 100 million years, a few hundred million years, and then it turns over again and has another, basically break in the power spectrum. And it's quite interesting that, the slope here is roughly 2, and the break happens roughly at 100 to 300 million years. And so, I don't want to go into the details because I think there's a lot of work ahead of us to understand the features in the power spectrum in these simulations in much more detail. But the key feature here seems to be that, there is an additional break, and it seems to be, the order of 100 to 300 million years. If I would just, put it on to what I talked to you about analytical modeling, this would somehow translate to a correlation length in the GMC model of roughly 20 million years. And of course, in the future, it would be nice to understand really the life cycle of GMCs in such simulations and understand, basically, are the GMCs really living for that long, or are there other processes, such as dynamical processes that act in galaxies as well, that could introduce features in the power spectrum. An additional thing to investigate in the future is, of course, the time dependence. You see that at early cosmic times, the power spectrum, basically the fluctuations here are overall larger than here at more recent times. So it would be also very interesting to understand, the early phase of galaxies versus the later phase in the power spectrum of galaxies. One of the last points for dark matter accretion histories now. So in illustrious TNG, we were also able to compare, basically just looking at the dark matter itself. So this shows you the power spectrum of the dark matter accretion histories. And you can see basically that it's rather featureless, has roughly a slope of 1. And it's quite neat that, basically there was a paper early this year that computed the power spectrum for dark matter accretion histories analytically. And they found a power spectrum slope of roughly 1. So this is quite consistent with what we find in these numerical simulations. Now, of course, the question is, okay, how important is this dark matter accretion history in shaping the star formation histories of galaxies? And what we can compute now is looking basically at the coherence, between the star formation history of the galaxy as well as the dark matter accretion history. And so this coherence basically show you how coherent these two signals are. And you can see that basically when we do this coherence analysis, we find that, basically nearly no mass dependence, and the star formation histories are basically coherent with the dark matter accretion histories only on the longest timescales. Okay, so this means that on short timescales, we really have these baryonic effects that dominate the star formation histories in these simulated galaxies, whereas on these longer timescales, the dark matter accretion histories and their overall shape plays a more important role. And that's why I was also saying that maybe it's just a coincidence that models that are able to reproduce the scatter of the star forming main sequence that are heavily related on dark matter accretion histories. This may be just a coincidence because basically the scatter of the dark matter accretion histories and the scatter in the main sequence is the same, but really physically, probably the short-term fluctuations are really, driven by short-term fluctuations coming in from baryonic physics. Okay, so now let's try and go and see what we can do observationally. So this was actually before we did all of the theoretical discussion, but basically investigations. So I show you here some results that Nevin and me have been basically putting together in the last year. And so what we assume basically here is that the power spectrum has this kind of shape. So we assume basically a simple broken power law. Again, the motivation there was not really based on theory because there was not really a theoretical prediction at that time. But the motivation was that the star formation history is somehow correlated on these shorter timescales. And then there is a break in the power spectrum. And on the long timescales, we just assume it's basically white noise. So it's basically uncorrelated. So the star formation history knows of the past history. And then after some timescale, the star formation history of the galaxy should lose its memory, basically. And so with this parametrization, we are able to describe, a wide range of different star formation histories about the star forming main sequence. You can see here, when we have a lot of power on short time scales, star formation histories are bursts. This means you have a short break time scale and the slope is rather shallow. So in these star formation histories, there's a lot of burstiness. And then when we increase the slope, we make it steeper, or we move the break to longer time scales, you can see that the star formation histories are overall smoother. And so how can we go now and measure this? As I said, we cannot, unfortunately, follow individual galaxies and construct these nice star formation histories. So what we need to do is we need to look at an ensemble of galaxies. And so that's why we look at the scatter of the star forming main sequence. And so if we would be able to look at an individual galaxy, this would look something like this. So what I show you here is the distance from the star forming main sequence. This is, real star formation rate. And the gray, curve shows you the intrinsic star formation rate, while the colored curve shows you basically as we would see it seen by different star formation rate tracers. So this is a star formation rate tracer based on H alpha. This is far UV, near UV, U band, and then going to the infrared, UV plus infrared. And you can see that, basically H alpha is able to trace these up and downs quite well. And so you can see that we are moving up and down the intrinsic curve, and we follow quite well with H alpha. If you go to something that is, basically sensitive to these longer time scales, you can see that you're smoothing out the star formation history much more. And so basically here, we are not just basically getting smaller scatter in the star forming main sequence, but also you can see that the curve nearly doesn't drop below 0 anymore here. So this basically means that we get an overall bias. And so this is interesting because it depends also on the burstiness itself. So burstiness increases to the left here. So on the right, we have rather constant star formation histories, so rather smoothly varying star formation histories. And in those cases, because the star formation doesn't change quickly, you basically average, basically the average over short time scales and long time scales, you have very similar results. And it's basically all very consistent with this intrinsic distribution about the star forming main sequence. On the other hand, when we go to, bursty star formation, only H alpha is able to get basically these bursts. And you can see that when you have very bursty star formation, you basically, this is the intrinsic distribution about the main sequence. And then H alpha will be slightly biased, to higher values, as well as it will be basically having a slightly smaller scatter, but still it's kind of closer than all the other indicators. You see the other indicators, especially the ones based on longer wavelengths, those usually are having a much smaller scatter. And so what we did then, assuming basically ergodicity, so basically we take a galaxy sample, which we believe has the same power spectrum, and basically probes, these time scales from the star formation indicators at different parts of the time series. We basically use, therefore, a galaxy sample that is well constrained in stellar mass, so a small, mass spin around the Milky Way mass, and also only star-forming galaxies. And so when we do this, we basically get this kind of constraints for the slope, as well as the break time scale. And so you see here, the coloring shows you different, the scatter ratio between, for example, what we measure in the U band versus UV plus infrared. Because these star formation tracers roughly probe the same timescales, the overall constraint we can get on these parameters in the power spectrum are not, that good. So they're, very broad constraints. And then we have also, things such as, for example, the UV plus infrared and H alpha gives a much tighter constraints. And combining all of these constraints together, you get this dark region here. And so you can see that somewhere, the break lies somewhere of the order of between maybe 100 to a giga-year. Now, we also assume, if you assume, for example, that the slope has a slope of 2, as again, this is motivated by the theory now, but I would say that, at that time, we just had an educated guess. Basically, if we do this, then we would get a constraint on the break of roughly 300 million years. So this means that the star formation histories in Milky Way-like galaxies decorrelate roughly on the time scale. And again, this is, to first order kind of roughly consistent to what, something like a fire simulation would predict. And I was quite surprised to see that. And of course, there's much more work ahead of us for this. So we basically want to constrain the power spectrum not only at redshift 0, but also move to earlier cosmic times. So now I would start talking about morphology and quenching, and I think we are up with the time, so I will move forward in slides. But of course, I'm very happy to talk more of how this is all related to, for example, bulge formation and also quenching at later times. And maybe I would just highlight what's kind of ahead of us very briefly, and then conclude. So what I show you here, what's ahead of us, for me at least, Cello VSD, I'm very excited about it. When I started my postdoc, I hope that I worked on that, and I'm working on it, but it's not flying yet. I hope soon. Of course, I'm very interested in this epoch here and try to understand star formation in those early galaxies. And thankful, to a better spatial resolution, also more infrared coverage, we'll be able to constrain the stellar mass and star formation rates of those galaxies in much, much greater detail. And we learn a lot about the morphology of these galaxies, but also we will learn about star formation basically in the first galaxies. And I'm very excited to learn more about the star formation process and how it's different, for example, from redshift 0 at these early times. Now, there's also a lot of work we can do constraining numerical models from this. So what I show you here is the stellar to halo mass relation as a function of halo mass. And so basically, this is our analytical model I showed at the beginning of the talk. And you can see these are currently numerical predictions for how much stars form a given halo mass. And you can see that different simulations are basically all over the place. So there is a lot of scope in constraining numerical models by just measuring, for example, stellar masses. And then on longer time scales, of course, ELTs, including GMT, will really, be a game changer for, the spatial resolution in high redshift galaxies. So for example, here at redshift 2, currently with HSD, we are able to basically, zoom in on and find some of these massive star-forming clumps that I briefly mentioned. With something like an ELT or GMT, we're able to really start resolving, the details of the GMCs in these redshift 2 galaxies. And for quenching and the cessation of star formation, we will be able to really space resolve age metallicity gradients in these early galaxies. So this is what I will skip. So I come to the conclusion. So I showed you at the beginning that star formation on global scales can be really related to the assembly of dark matter halos. And so I think on global scales, a quite clear and I would maybe say simple picture arises. But then of course we see that star formation is really made, by small entities, right? And the question I think remains of how do these small scales couple to these larger scales? And we basically put forward the idea of the power spectrum density to quantify, at least in the temporal space, this variability of star formation. And we showed you with some simple models and also more complicated numerical models, trying to link these temporal variations to some of the underlying physics for star formation across small and larger scales. In particular, for this analytical approach, I show you that the breaks in the power spectrum correspond to the average lifetime of GMCs on short time scales. This is quite interesting because it might open a window to measure the GMC life cycle in galaxies that we are not able to spatially resolve. And then we also show you that in the intermediate and long time scales, the equilibrium time scale, basically, which is related to the depletion time and the mass loading, and the correlation time scale in the accretion onto the galaxy play important roles. I show you that the star formation histories at redshift 0, the star formation histories seem to decorrelate from Milky Way-like galaxies around 300 million years. I would like to show you at some point, maybe in the future, that oscillations also related to bulge formation and therefore to some of the morphological differences we see between star-forming quiescent galaxies today. And as I mentioned very briefly, there is also much science ahead for us with JWST and the ELTs. Okay, that's it. Thank you very much for listening and tuning in, and I'm happy to answer, of course, any questions.
Thanks, Sandro, for a very fascinating talk. So if people have questions, feel free to speak up or alternatively post in the group chat.
Hello, Sandro, can you hear me?
Yes.
Hi, this is Vadim.
Yes, talk.
I have a quick question. So do you show the comparison of dark matter only and with baryons for illustris? And by eye, it looked that features in the power spectrum were very similar, so which is, I guess, not surprising because cosmological so do not resolve the formation of cold gas and coldest forming gas. But did you look at something like this for fire as well? Because there you would see the difference.
Yes. So we didn't look yet into fire. I think this is exactly something to do. There is, I think, a lot to do. You see, so I think the key message from this work with Kartek was really to basically just get a first impression of how the power spectrum densities look like in different simulations. And the main conclusion there is that basically galaxies or these simulations basically show a lot of diversity. And therefore, I would say that it's a very interesting parameter space to go on and basically try to constrain observationally because it seems to constrain numerical models. The question, of course, here with related to dark matter is really indeed that that TNG seems to have similar features. Overall, the slopes are quite different, and we look at actually the absolute difference between the PSDs in the paper. I'm happy to show it to you offline. I think the interesting plot here is really showing you the coherence. And so even though the features seem to be roughly similar, when we look at the coherence between these two time series, they seem to be really not coherent on these shorter time scales and only really coherent on these longer time scales.
We have another question from Benedict. Please go ahead.
Fantastic talk, Sandro. I really like the new stochastic model. This is super cool. One question I had was, when we looked at sort of the star formation histories in a more functional sense, we found that they can be described by similar functions as the dark matter halo accretion histories, but there is sort of a time offset. And this can be quite a substantial offset, right? Sort of a gigayear, the idea being you accrete, say, very quickly for a while, but it takes a while for you to actually make the stars. And I'm wondering if something like that, if it exists, would show up as sort of almost an anti-correlation in your analysis, or at least no correlation, which is sort of consistent with the plot that you're showing on the right. Have you tried sort of doing a time offset between the two and seeing if you can increase the correlation?
Yeah, so this coherence basically takes out this phase shift that you're talking about. So indeed, so the coherence basically takes out this kind of phase shifts that could be in the data. So we shouldn't worry about this. But indeed, you're right. I mean, it would be very interesting to just look at the, if there is any phase difference in these, in for example, the dark matter and the in situ star formation. I'm sure we've looked into this, and I can try to figure out again what the results there were. But I would agree for sure that your work on showing that the star formation histories overall go with the dark matter, right, slightly offset, are very consistent with this here, right? In the sense that basically the star formation history seem to really be dominated by this long time scale and oscillations that come in from the dark matter. So basically, higher accretion rates at early times and then a slower decline. And so I think that's I would say a quite makes I think a lot of sense. Yeah, and in detail for the phase shift, I think we can look into this in the next few days if you want. Yeah.
Sonak, you're next.
Hi, Sandro. Thank you for a very interesting talk as usual. I had a quick question, which I'm not entirely sure actually makes sense, but using the power spectrum, sort of the PSD analysis, do you think it's possible to eke out, maybe eventually from observational data, but maybe to start with from simulations, things like what the role of perhaps less well understood processes in galaxies, like the effects of turbulence and stuff like that, is on the star formation history of the galaxies, based on, say, like the coherence or decoherence timescale of the power spectrum?
Yes. It's a very good question. Yes, actually, I started a project with Vadim, was the first question. We're kind of trying to figure out how important is the turbulence in as well as dynamical processes within these systems. Because indeed, so the analytical prescription we did, or looked into is very simple, right? It's basically having a model for drawing GMCs, and then has some kind of an accretion inflow rate. But of course, there is much more to galaxies. And of course, we could start thinking of more complicated models. And we basically added a simple dynamical deriver in the model as well at some point, which we discussed in the paper. But there is indeed much more complicated physics. And indeed, I think numerical simulations, and I'm motivated to talk with anybody who runs these simulations and is interested to look into this in more detail. But indeed, I think numerical simulations are able, hopefully, to tell us a bit more about things that are acting on many different scales, such as turbulence, for example, that are able maybe to link these kind of small-scale star formation feedback processes onto larger scales. And so, from a philosophical point of view, I'm wondering, there is indeed, my question is how important are these small-scale, let's say, more chaotic drivers into the imprint onto a star formation histories on global scales. I think numerically there is a bit of a limitation there. I think Shai Ganel, as well as there's another paper by Keller and et al. Last year, where they basically try to understand how this chaos on the smaller scales basically relates to larger scales. And I think there is a bit of a numerics there, right? So there is basically this so-called butterfly effect that when you perturb the stellar particles or the gas particles, by sub-precision basically of simulation, then you basically end up with quite different looking galaxies. And so at least in numerical simulations, there seems to be this, connection between the small and large scales. My question is, how can we go about this in observations? And I think maybe the power spectrum might help us there.
All right, thank you. That sounds very interesting. Cheers.
Let's take one last question from Anthony.
So this is a comment. It seems to me that the star formation in the outer parts of massive galaxies is more like star formation in dwarf galaxies than it is like the centers of those same massive galaxies. So chunking systems in as galaxies may not be the best way to really understand the physics of star formation, because you know, a lot depends upon the local stellar density and the local density of molecular material, and of course in large galaxies that varies from very, very dense in the middle to not very dense at all in the outer parts, which is just like essentially a dwarf galaxy.
Yes, yeah, thank you very much for the comment. I think that's of course very true, and I'm very interested exactly in that. You know, like the models that I showed you is basically treating the galaxy as one entity. But of course, there is a lot of spatially resolved information, in particular in observations at low redshifts, and also in the models. And we started looking into, at least in the numerical side, to see if there are differences in the power spectrum when you look at the central part of a galaxy versus the outskirts. And there are indeed differences. So I think there is, of course, more to what I've just shown you. And so I think that's something to understand. Can we learn something when we just look at the power spectrum on the integrated entity, basically? Or do we need to really split up into the different parts? And so at least when we look at, for example, something like the fire simulations, they show that, for example, the GMC lifetimes measured in the simulation seems to be rather constant as a function of radius. Now, this is just a model, but this would then, you know, maybe reflect that we can maybe learn something about, you know, GMCs when we just look at integrated constraints. But I totally agree that we have to look into spatially resolved data. And of course, you know, that the part that I, you know, was not able to talk about is exactly how this relates to, you know, having different components in the central parts, such as bulges, to the outskirts. And I'm very happy to talk more about this offline as well.
All right, so thank you, Sandro, for a very great talk, and look forward to hearing more about your work in the future. All right.
Yeah, thank you. Thank you all for zooming in, yeah.
So everyone, have a great rest of your day.